Uh, Thank you very much for the invitation and the lovely introduction and organizing this workshop, which, from the variety of talks we've seen, it's the sort of thing that we like to do in Santa Fe as well. So it's an honor to be giving a lecture series named after one of my heroes, Alan Turing, and also, at least starting tomorrow, in an auditorium named after another one of my heroes, Srinivasa Ramanujan. And of course, as you all know, both of these people were incredibly original thinkers, and they also both dealt with a lot of adversity and prejudice, and they also both died far too young, and we can only imagine what we would have learned from them if they had lived longer. So sometimes, when we think of our heroes, I really wish we could go back in time and just say thank you for opening up new vistas of mathematics to us and let them know how much those who came after them appreciate them. So anyway, I'm going to be telling you about an analogy between statistical inference and statistical physics. And this analogy has grown up around a collaboration between computer scientists, physicists, mathematicians in probability and statistics and combinatorics, people in machine learning, a collaboration which has been going on much longer than I've been involved in it. So overall, statistical inference means the process of looking for patterns in noisy data. So we live in the age of big data. I saw somebody with a t-shirt saying, "My data is bigger than yours." So yes, we have big data, but we need to remember that a lot of the data sets we have are actually very noisy and very incomplete. And relative to the number of variables that we're trying to learn about, in some sense, they're actually not so big. So for instance, in genomics, you might have 1,000 different rats, but in each rat, you're looking at 100,000 different genes or something. And so it's very high dimensional data. So relative to the number of possible patterns we could be looking for, or different correlations we could be looking for, in some sense, the data is actually quite sparse. So what we've learned is that, at least in a theoretical setting where the data is generated from certain models, there are phase transitions, where if the data is too sparse or too noisy, it suddenly becomes impossible to see the underlying pattern, or even to tell if there is an underlying pattern, even to distinguish the data from random noise. And I think this is interesting because it helps give some mathematical backing to, for instance, the crisis in genomics and biomedicine, where we know that between the statistics and things like publication bias, sometimes we see patterns that are not really there, and publish patterns that are not really there. And this is a big debate now in science. So these phase transitions, on the one hand, give us negative results. They give us fundamental limits on our ability to see patterns in data. But we also want positive results. We want algorithms which are optimal in the sense that they succeed all the way up to these limits. So I'm interested in both those types of results. And it's also interesting that in some cases it seems that we get different thresholds depending on whether we phrase this problem information theoretically, where I give you all the computational resources in the world, all the time in the world, and I let you do anything you want with the data set, versus the thresholds we can achieve if we're limited to efficient algorithms, polynomial time computation in computer science parlance. Finally, maybe the most important thing about all of this is just the joy of interdisciplinary work. And there's been a wonderful exchange of ideas where physicists have taken intuition and experience from their studies of disordered materials. They've done high-quality numerical experiments, and based on that, this has inspired a structural picture of what's happening in these problems. And then much of that picture has now been made mathematically rigorous through beautiful work in random graphs, random matrices, and many other techniques. So it's been a wonderful exchange between these fields. All right, so I'm gonna start. This talk is hopefully going to be very accessible. We're at the end of a long day for everybody, so I hope this will be a friendly talk. I want to start by illustrating this analogy with one of the simplest and most common statistical procedures. It must be that tens of thousands of scientists do this every day. So here you go. I have a bunch of data points, x1, y1 through xn, yn. And it looks to me as if there's kind of a straight line there, plus some noise. So what do? How do we choose the slope and intercept of that line? If our model has two parameters, a and b, and y is supposed to be ax plus b, how do we estimate a and b? Well, what we almost always do is minimize the squared error between the model and the data, the sum of the squares of these deviations between our model and the data points. But why do we do this? Why should we do this? Why should we believe that this is a good way to estimate A and B? It's mathematically simple. It's a convex problem. There's a million software packages that will do it for us instantly. So it's very convenient. And besides, everybody else did it. But why should we do this? And under what circumstances should we do this? So, well, what's really going on, at least one justification for this, is that our actual model is that the data is generated from this straight line, but that there's also some random noise, W, and furthermore, that we believe this noise is normally or distributed, it's a Gaussian distribution, where the probability is e to the minus 1 over twice some variance times the noise squared. If we believe that, then, assuming that all the data is generated independently, the probability of getting the data is the product of this probability of each point, which is just e to the sum, and look, there's the sum of the squares. So, if the noise is Gaussian, then Bayes would come along and say, as long as you don't have a strong prior opinion of what A and B would be in the absence of any data, for the experts, a flat prior, then the probability, the posterior distribution of our parameters given the data would be proportional, that little alpha thing means proportional to the probability of getting the data given the model. And then the least squares estimate is also what people call the maximum likelihood estimate. It's the one which would maximize the probability of getting the data, which means minimizing the sum of squares. Okay? So this is one justification for sum of squares. And now we should all be thinking, gee, do we think the noise is Gaussian? Do we think that every point has the same variance of noise? And so on. So we should be questioning whether this is the right procedure. Anyway, what does this have to do with physics? Well, let's define the energy as minus the log of the probability, which is then simply the sum of the squares with 1 over twice the variance in front. So if you remember your high school physics, this is like saying there's a bunch of little springs attaching a stick, which represents our model, to the data points. Because if you have a spring of stiffness K and you stretch it by a distance x, then the amount of energy stored in it is 1/2 kx squared. So then, maximizing the probability is the same as minimizing this energy, and the least squares estimate is what in physics we call the ground state. It's just the lowest energy state of the system. Good, well, you know, what if the energy were different than this 1/2 kx squared? And why might we want it to be different? So here's a nice example. So every once in a while in real data sets, you have outliers. So you have a bunch of data points which look like a model plus Gaussian noise, but then you have a few data points that are pretty far from your model. So for instance, this is true in a famous data set consisting of different measurements of the speed of light. And the intuition is here that some sources of error in the laboratory are roughly Gaussian. They're sums of independent things. But every once in a while, you know, your lab assistant bumps into the apparatus, or the rat had the sniffles that day, or, you know, someone forgot to turn on the electron beam, or something like that. So there are also occasional data points that are quite far from the model. So what do you do then? Well, there are many ways to do this. There's this whole field called robust statistics that tries to deal with outliers. And so, for instance, the particle physicists already, they know what they want to do. But here's another thing you could do. You could say, well, my noise model is not Gaussian. I'm going to assume that the probability of the noise goes to 0 more slowly as we get out into the tails than it does in the Gaussian, right? Because the problem here is that the Gaussian distribution is incredibly surprised if you have a data point 10 sigma away from the mean. It's very surprised and upset about that. And physically, it means that this spring has an enormous tension on it if you stretch it that far, and this will pull down your stick and skew your estimate. So if we adopt a different noise model, pardon me, here we are in the modern age. Okay, you can go away now, good. All right, great. So physically what this means is that the energy would not grow quadratically as we move away from the mean, but it would, for instance, we could have it level off and become linear, and the force is the derivative of the energy. So that means that rather than the force getting stronger and stronger as we stretch the spring, it would be more like chewing gum, right? Something soft, where when you stretch it far enough, then it gets softer and exerts less of a force. So we could adopt this noise model. We could argue about whether it's a good noise model. It would give us a different procedure, though, which would be less skewed by outliers. Okay. So I don't know if you like this physics picture yet, but there's another thing that's important, which is that another thing that Bayesians say, and by the way, I know that there are these huge theological disagreements between the frequentists and the Bayesians. I think I'm a sort of moderate Bayesian, at least for the purposes of today's talk. But so one of the things that Bayesians say, they basically say two things. One is that you should adopt a model for where you think the data came from. It's like, come on, you have a model. Admit it and write it down. Okay, that's one of the things Bayesians say. The other thing that they say is that, of course, you would never commit to a single estimate. That would be dishonest. These estimates are uncertain after all. So what you should do is instead advertise the entire posterior distribution of the estimates given the data. Again, this is not the only way to reason about uncertainty, but it's what we're going to be doing today. So Boltzmann says that, well, rocks like to fall, things like to be in low energy states, but when they're at non-zero temperature, then they're getting jiggled around by thermal noise, so occasionally they are in higher energy states by chance. And Boltzmann taught us how this probability distribution works at equilibrium. If you're at a temperature T, the probability of being in a given state goes down exponentially with the energy of that state, but how fast it goes down depends on the temperature. So for instance, at very low temperature, since we're dividing by something small in that exponent, it becomes very sharp. And then we're almost always concentrated on one of the lowest energy states, one of the ground states. On the other hand, at very high temperature, this becomes a rather gentle exponential, until at infinite temperature, we'd be equally likely to be in every state. So because we defined the energy as minus the log of the probability, so then the posterior distribution is this thermal distribution. And if you remember on the previous slide, we had 1 over the variance up there in the exponent. We could phrase this in several different ways that are equivalent. One is to say that the temperature is the variance, so that more noise means a hotter system. Or we could say, since the energy of a spring was proportional to its stiffness, we could say that the stiffness of the springs is 1 over the variance, so that a noisier system means floppier springs. I'm sorry I don't have an animation for you of this, but you should imagine this stick that represents our model kind of jiggling around, and that the typical places it would be then representing our uncertainty about the slope and the intercept. So what this gives us, after we define the energy this way, is an energy landscape. In this case, it's a very simple landscape with just 2 dimensions. We just do these 2 parameters, A and B. And it's, if you complete the square and so on, it's a quadratic function with the minimum at the most likely value. And then your posterior distribution is this thermal distribution, which in this particular case has just one hump at the most likely value. Okay, good. So there's the analogy between Bayesian inference and equilibrium statistical physics. Now, I promised you phase transitions, and in this particular case, it's not as if when the amount of noise exceeds some threshold, we suddenly cannot do anything. You know, our confidence, our uncertainty about the estimate would degrade as we made it noisier and noisier, but there's no sharp threshold. So now I need to introduce you to a model where there's a sharp threshold. And about half of you know this model very well, and maybe half of the other half, but here it is, the Ising model. So in a block of iron, roughly speaking, each little atom of iron acts like a tiny magnet on its own, and it interacts with its neighbors. And in a ferromagnet, ferro meaning iron, they would prefer to be the same as their neighbors. And so when their interactions are strong enough, or the temperature is low enough, which amounts to the same thing, then a large majority of them line up the same way. Not all of them, but most of them will line up the same way, and then the block of iron has a strong magnetic field. So let's write this down in terms of an energy function. So we will give each location in each atom a little variable called a spin. It's either +1 or -1. And in this toy model of magnetism called the Ising model, things only interact with their nearest neighbors. And since we want the energy to be lower when they agree with their neighbors, we're going to put a minus sign out here, so that if these are both +1 or both -1, then the energy will be minus J. J will be a positive constant that just means how strong the interaction is. Whereas if they're opposites, then we would get an energy of +J from that pair. All right, so that's our energy function. I mean, by the way, just culturally, it's kind of interesting that in some scientific fields, when you define a model, you do it by defining the dynamics. In some fields like economics, you define conditions for equilibrium somehow. In physics, the way we define a model is usually the energy function, and then the dynamics is defined in terms of that. So now, from an optimization point of view, if I asked you what is the lowest energy state or the most likely state, this would not be a very interesting question. Make them all up or all down. That is the lowest energy state. But of course, if I sample the system, most of the time I will not be in that most likely state because there are exponentially more states that have some mixture. So at equilibrium, I'd like to know what is the typical value of the magnetization. So here we'll take the average of all the spins. Since it would be equally likely if we flipped everything over, we'll take the absolute value. So intuitively, as we increase the temperature, the magnetization would go down. At absolute 0, it will be 1 because they'll all be aligned the same way, but it'll decrease somehow with the temperature. But how? Well, Pierre Curie, who you might have heard of, he was married to Marie, found that there is in fact a critical value of the temperature where the magnetization suddenly drops to 0. It does not degrade continuously as you go to higher and higher temperature. Instead, there is a phase transition. And what's happening here is that below this transition, you have a clear majority of ups or downs with small islands of the minority floating in it. And the typical size of an island is, the average size of some constant. But above the transition at large scales, it really looks like white noise. Or like, a television screen when there used to be this thing called television, and when there wasn't a show on, it looked kind of like that. Anyway. So now above the transition, in fact, if you measure the correlations, if you look at the average of the product of two spins, a distance r apart, this correlation decays exponentially as a function of r divided by some characteristic length, so that distant spins are effectively independent of each other. So somehow what's going on here from an information or computation point of view is that above the transition temperature, the system it's incapable of transmitting information over long distances. It's gotten too noisy or the interactions are too weak, and it just can't connect the variable over here with the variable over there. So, we might imagine intuitively that something similar could happen if we defined a similar model, but as an inference problem. Okay, good. So imagine that this y-axis, instead of the magnetization, was some notion of accuracy. So for instance, we'll talk about this problem of community detection in networks, where we're trying to label nodes in a network according to what group it belongs to. Then the magnetization could be the fraction of nodes that are labeled correctly. And the x-axis would be some measure of the noise in the data, or perhaps its sparsity. And again, we would have some phase transition where our accuracy would suddenly drop to 0, and above here we would be able to do no better than chance, no better than a random coin flip. We would be completely unable to classify the nodes of the network. So that's the idea. Now, the other thing that's going on here is the shape of the landscape. So the least squares problem had a landscape with a single peak. This is sometimes called a Mount Fuji landscape, right? So it's an easy optimization problem. The Ising model has 2 peaks. That's some mountains we see from the porch of the Santa Fe Institute. Because there's the mostly up states and the mostly down states. So its distribution has 2 peaks. But in a computationally hard problem, we expect there to be exponentially many peaks in a high-dimensional system. And in physics, this happens in what's called a spin glass, which is a generalization of the Ising model, where each pair of vertices has a different interaction. And indeed, some might be positive, a ferromagnetic interaction where they want to be the same. Some might be negative, an anti-ferromagnetic one where they want to be different. And so you could imagine that you could have many local optima in this setting where each local optimum corresponds to, in computer science terms, having solved part of the optimization problem, but not some other part. So we've made some of these interactions happy, some of them are unhappy, some other subset is a different local optimum, and so on. And you could imagine it would be very hard to find your way around this landscape. So now imagine that these interactions are somehow set by a data set, and that one of these local optima somehow corresponds to the true pattern we're trying to discover. Well, how could you find which one is correct? Can you find it efficiently? That looks like it might be hard. This type of bumpy landscape is also what we often see in NP-complete problems, which are problems where if I show you a solution and I tell you this is a good solution, you can check that it's a good solution, but you're in an exponentially you're in an exponentially large space, and it's a very high dimensional space, and it's very hard to find those solutions. And we believe that no efficient algorithm exists, at least if the example of the problem is designed by a clever adversary, which is not going to be the case here, but still, I mean, we might worry these problems are hard. So we could ask, can we find the true optimum efficiently? We can also ask, can we find it at all? So even if I magically give you access to this entire distribution, even then, can you find which peak is correct in some sense? All right, good. So now that we've sort of philosophized about this problem, let's zero in on a particular problem where these phenomena occur. So finding communities in social and biological networks is a popular pastime. So this is a network of political blogs from the 2004 US presidential election from 12 years ago. At least some of them were still linking to others in the other group. Now I think these might be 2 totally separate things. So I forget which are the Republicans and which are the Democrats, but as you know, for better or worse, people like to link to others that agree with them. So in that case, those are our communities. We can have other sorts of groupings as well. This is a food web that a colleague of mine put together from a lake. So rather than two factions here, instead we have groups corresponding to different trophic levels, as the ecologists say. So these bottom nodes are basic resources, then there's a layer of herbivores, then there's a layer of plants, and then herbivores, and then carnivores, with some cannibals up there at the top. So this is another type of grouping that could exist in a network. And then here is a network of adjacent words in the novel David Copperfield, where in this case there's a lot of edges between the adjectives and the nouns, because in English, adjectives come next to nouns, sometimes next to other adjectives. Nouns are not usually next to other nouns. This third group was words like light that work as both nouns and adjectives, and the algorithm put them in there because it wasn't sure what to do with them. Okay, so, all right. So there's a pretty general model for all of these types of groupings, and it's called the stochastic block model. So now here is one place where I'm going to depart from the orthodox Bayesian ideology. I do not believe that any real network is generated by this model. Okay, so in other words, I think this model is wrong. I'm going to use it to fit networks anyway, and I'm going to appeal to the old saying that all models are wrong, but some are useful, at least some of the time. And as you're about to see, this model is extremely simple and naive, and there are lots of things about networks that it gets completely wrong. But if your goal is this community detection problem, where you're trying to clump nodes into groups, for that particular application, it seems to do pretty well, even on real-world networks. So here's the model, and historically, by the way, it originated in the sociology community in the 1980s. It's been rediscovered many times. Some people in computer science call it the planted partition model. Some people in physics call it the inhomogeneous random graph. So lots of people have thought of this model. Without further ado, there are k kinds of nodes. And for today's talk, k will be some constant like 3 or 7. And there is some k by k matrix, P, which tells us the density of edges between the different types of nodes. So specifically, T sub I here will be the type of node I. And if I is of type R and J is of type S, or belongs to group S, then there will be a link from I to J with probability P sub RS. So that's the whole model. If you're familiar with the Erdős-Rényi random graph, that's the case where k equals 1, and all nodes are connected with the same probability P. So all we're saying is that the probability depends on their types. Now, the phase transitions that I'm interested in live in the sparse case, for the physicists, the dilute case, where the probability of a connection is order 1 over n, which means that as I scale up the graph, the total number of neighbors that I'll have, typically, or on average, will be some constant. And this seems to be reasonable for a lot of real networks, but it's also where this problem is tricky. Because if you only have 3 neighbors, then even if I knew exactly what group your neighbors belong to, I would still be pretty uncertain about what group you belong to. So this is the regime in which these phase transitions live. Now, a popular special case is kind of like the one I showed with the blogs, where there's one probability Cin over n that you connect to others within your group, and another probability Cout that you connect to people outside your group. And it's popular to usually assume that Cin is bigger than Cout. So this is the ferromagnet, where you're more likely to be in the same group as your neighbor. In other fields, it's called assortative or homophilic and so on. Okay, good. Now, let's write down the probability and the energy the same way we did before. So if I fix the labels of who's in what group, in physics we would say for a given spin configuration, a given state, then it's easy to write down the probability that I would have a certain network. It's just a product over all pairs of the probability they're connected if they are, and the probability that they're not if they're not. So there you are. There's the probability. And then the energy, we'll say it's minus the log of that. These products turn into sums, and we get this sum over pairs. And now if you look at this, this is pretty much just like the Ising model, because at least if Cin is bigger than Cout, this term will encourage neighboring pairs, these are the neighboring pairs, to be the same group, to be in the same group. There is also these weak interactions between all the non-neighboring pairs. I say that they're weak because if p is order 1 over n, then log of 1 minus p is also 1 over n. But we don't want to ignore these completely. For instance, you know, if Ravi and I didn't know each other, given how many friends we have in common and how we are interested in a lot of the same things, that would be strange. So the lack of an edge between two people does give us a little bit of information about them. It slightly increases the chances that they belong to different groups. So these are weak anti-ferromagnetic interactions between all pairs that, for instance, will make sure that we don't put everybody in the same group. Because if we had only these interactions, then we might as well put everybody in the same group. All right, good. So there's the physics of the block model. What do we do with this physics? Well, again, my computer scientist friends, they like to optimize things. So they would say, all right, well, what's the lowest energy state? What's the highest probability state? But maybe you don't want to do that. All right, that might not be the right idea. So here is a beautiful community structure suitable for the cover of Science or Nature. I have taken a network and I've colored the vertices red and blue so that only about 11% of the edges cross from one group to the other. Only 11%. The other 89% of the edges are within the groups. So you would say, good community structure. Perfect for, you know, you definitely found something real here. The problem is this graph is completely random. Specifically, it's a random 3 regular graph, which means everybody has 3 neighbors, but I made it by wiring up those neighborhoods in a totally random way, who's connected to whom. So there are really no communities here. So what's going on? Well, what's going on is that here is one ground state, but here is another. That's the limit of my special effects in the talk. So this ground state has an equally low energy, an equally high probability, but as you can see from the colors, it's completely uncorrelated with the one we had before. So part of the reason I got into this field is that there are lots of community structure algorithms out there packaged with graph visualization packages and so on, and people say, oh, I have a network, I'll run this algorithm, I get a structure. But the vast majority of these algorithms don't give you any guarantees about whether what they found was statistically significant in some sense, or whether it was there just by chance. And in particular, whether there's some other totally different structure which looks just as good. So when you have a situation like this where you have many local optima with nothing in common, then I would argue thinking of this as an optimization problem is just wrong. Because what do you care, even if you could find the optimum thing, which, like I said, might be computationally hard, it doesn't tell you anything real if there are other optima, local optima, that are almost as good, which are totally different. Okay? So, and this, our statistician friends have a name for this. We're overfitting here. We're finding more structure than is really there in the data. So, a quick sermon about overfitting. So, you know, when we were evolving, it was probably worse to think that there isn't a tiger there when there is than think that there is one when there isn't, okay? So with tigers, false negatives would be worse than a false positive. So we are great pattern matchers. We see patterns everywhere, even when they're not there. I mean, electrical outlets look like faces and so on. So we're very good at finding black cats in dark rooms, even when they're not there. And so are our algorithms if we're not careful. So it's always tempting to fit with a fancier model, because with a fancier model, you can get a better fit. You should hire me as your financial advisor, because here is a set of stock prices, and here is my model with 10 parameters, and it fits the data perfectly, and you should buy this stock right now, because it's about to go through the roof. But of course, you know the rest of the story. This is the actual data. And what I should have done is a less fancy model with fewer parameters, which does not fit the data I have as well. And when you do not fit the data you have as well, you often do a better job at fitting the data you don't have. Okay, so All our statistician friends have been telling us this for about 100 years, but let's be honest, most of us are still not listening. And in a lot of areas of science, we are still fitting data with nice fancy models and saying, look, I got a really good fit. Okay, so the problem here is that our fancy model wasn't fitting the underlying process here, which was just a parabola. It was fitting the noise. It was fitting the stuff which was only there by chance. And that's what we want to avoid. We don't care what's there by chance. We want to understand the underlying process. Okay, so end of sermon. So in order to formalize what we can do in the block model, let's analyze the effect of a single link. How much information does a single link give us? So this will be the most technical slide that I will impose on you, given that it's after 4 o'clock. So again, let's suppose we have k groups. Let's suppose they're of equal size, so we have about n over k nodes in each group for simplicity. And let's suppose that our probability has this simple form, Cn on the diagonal and C out off the diagonal. And if you work it out, then the total average degree, the average number of neighbors that each node will have, is this, because, well, for instance, there are n over k vertices in your own group. You connect to them with probability Cn over n. The n's cancel, so you have Cn over k in your group on average, and then you get these contributions from the k minus 1 other groups. So that's the average degree. Now, suppose that all we knew was that here's a link I, here's a node I, here's a node J, and that there's a link between them. Well, then if you had a little k-dimensional vector, which was the probability distribution of I's group, I's type, then you could compute using Bayes' law the probability distribution of J's type, and it would be given by this little transition matrix, which is proportional to the probability that there is a link there, because that's how Bayes' law works. We need to normalize it. We divide by the sum of this column, but the sum of this column is just C there times K. It's just that numerator. So this is a stochastic matrix. So this is our transition matrix that takes us from one probability distribution to the other. Now, there's a nice compact way we can write this matrix. If we define lambda as this, which is in fact the second eigenvalue of this matrix, this whole thing is lambda times the identity plus 1 minus lambda times this flat matrix, which takes any probability distribution, forgets it entirely, and replaces it with the uniform distribution where you're equally likely to be in any group. So we can interpret this by saying, when we go from I to J, with probability lambda, we just copy J's group to I. Okay, so that's, if you like, when the group membership gets transmitted along the link. And with the rest of the probability, it's as if the link isn't there at all, and we set J's group randomly, uniformly. Okay? Now, why did I define this? Well, because lambda is now a kind of measure of the strength of the community structure. It's a measure of how strongly information flows from place to place in the network. And so if you fix lambda and then imagine keeping lambda fixed while we increase C, we increase the total average number of neighbors you have. Well, intuitively, this will make the problem easier because the more neighbors you have, then the more information I, the community detector, have about you. So we would expect this problem to get easier as C increases. All right, now, is there a phase transition as a function of C and lambda? And indeed, here there is. So let's start with two groups of equal size. Here's the situation. There's a threshold value of the total average number of neighbors as a function of lambda, the probability that essentially that the group gets transmitted along a link from one node to another. The smaller lambda is, the larger your average number of neighbors needs to be, and it turns out to be 1 over lambda squared. And in fact, above this threshold, the problem is easy in the sense that there exist efficient algorithms several of them. Belief propagation is a message passing algorithm. And then there are spectral algorithms. Turns out the standard spectral algorithms don't quite work, but you can fix them. And these algorithms are optimal in the sense that they succeed all the way down to this threshold. They succeed better than chance. And in fact, we believe belief propagation is really optimal in that we think that in the thermodynamic limit, the limit of large networks in this model, it achieves the highest possible accuracy. The same accuracy you would get if you had an infinite amount of time to do your computation and to figure out the labels, the posterior distribution of the labels given the network. Below this threshold, this problem is flat out impossible. I don't mean that there's no algorithm or no efficient algorithm, it's information theoretically impossible. So no matter how much computation time you have, asymptotically you can do no better than just flipping coins. And what's going on is that this is a bit like the Ising model above its critical temperature. Information simply does not travel very much from place to place. When we don't have enough neighbors, the system is too dilute, too sparse to transmit information over long distances. So in fact, it's worse than that. You can't even distinguish a graph made by the model in this range from a completely random graph, an Erdős-Rényi random graph where there are no communities. So people in statistics like to talk about a null model. A null model is a kind of baseline where the structure you're looking for is not there. And so if you cannot even distinguish the structured model from the null model, you cannot tell which one generated the data, well, you should be pretty nervous then. You have no reason to think that there is structure there if the null model is just as convincing a way to generate the data. So good. And this result was first conjectured in the physics literature, and then over the past few years, it's been made mathematically rigorous through this lovely interface I was describing. It turns out that when you have more groups, some additional phenomena appear. So you might think, 2 groups, 5 groups, who cares? But it turns out that as soon as you have 4 or more groups, there are regimes that look like this. So there is still this easy regime when the graph is dense enough. There is still down here the information theoretically impossible regime where you can't do anything. But then there's this interesting middle ground where we know that it is possible to identify the communities information theoretically. So if I give you all the time in the world to do Bayesian inference, you can find them. But we believe that it is computationally hard. So we don't know that because if you've heard of the P versus NP problem, it could be that all such problems are easy, but we don't believe that. So there are some good reasons based on the physics of the problem to think that in this regime, it really takes you exponential time to find the communities. So for instance, it could be that, let's see, look, there's some glass up there. So the physicists have all heard this story before. So there are a lot of materials that want to be perfect crystals. They want to be perfect crystals. The crystalline state would have a lower energy than the state they're in, which is an amorphous, glassy state, which at small scales looks more like a liquid than a crystal. But they never find the crystalline state because they're stuck in, let's see, I don't know how much terminology to use. They're stuck in a kind of basin of attraction, a bunch of states that are locally stable, and they would have to get over a big barrier in order to find the crystalline state. So if we gave them the age of the universe, or if we cooled them very, very slowly from their molten state, they would find the crystal, but they'll never find it. And we actually think there's an analogy there with the inference problem in this range. There's also a regime below there where there are lots of clusters, but you really can't tell, even if I give you all the time in the world, you really can't tell which one is the ground truth, which one was used to generate the network. And so in this regime, you're really in danger of overfitting because the physics of the problem looks just the same in the block model and in the null model, the completely random one. Okay, good. And we know where this threshold, how it scales with lambda and the number of groups, and you can see from this log k over k here that when the number of groups is sufficiently large, this information theoretic threshold is below where we think the threshold for efficient computation is. And in fact, it happens already with 4 or 5. All right, so this was all just an advertisement for the next 2 lectures in the Ramanujan Auditorium. But first I have to tell you that a lot of the same phenomena also happen in another problem which thousands of people try to solve every day, which is clustering points, all right? So I mentioned this thing about 1,000 different rats and 100,000 different genes. I just made up those numbers, but I hope they're not wildly unrealistic. So imagine that you have m points where m is large, but they're in n-dimensional space where n is also large. So a lot of big data sets are this way. So they're large, but relative to the number of dimensions, they're rather sparse. So consider a regime where m is linear in n. So where m over n is some constant, okay? There are phase transitions that live there. So let's suppose we have k clusters and there's some Gaussian noise, and I won't introduce formal notation, but as you can imagine, there could be transitions which depend on how far the clusters are apart and how big the noise is. So if the clusters overlap a lot, it might be hard to find where the cluster centers are, to label the point according to what clusters they belong better than chance, or even to tell whether there really are clusters. So in this case, the null model is one big cluster, one big Gaussian, centered at the center of mass. So if I or nature hide behind this podium and I either generate the data points from a mixture of Gaussian clusters with 7 different clusters, or it's actually just one big cluster, can you tell which? Okay, if you can't tell which, then you should be nervous about saying that there are clusters. So indeed, there are phase transitions here, and we have, similar to the community detection problem in networks, a regime where if the number of clusters is large enough, we have this middle regime where it's information theoretically possible to find the clusters, but we think it's computationally hard. So a very, very basic inference problem with similar phase transitions. I mentioned PCA here. This stands for principal component analysis. This is a popular spectral algorithm for finding the clusters, but we can prove that there's a regime where PCA fails, but if you have exponential time, you can find the clusters. So maybe there's an efficient algorithm that succeeds in there, but all the algorithms we know of, including PCA, fail. All right, so just to conclude and to advertise the following 2 lectures, how are we going to prove these things? So, and I just, when I was in school, I loved the astrophysics class because you got to do everything. There was fluid dynamics, and there was nuclear physics, and there was statistical mechanics, and it was the same Chandrasekhar that this auditorium is named after, right? And there was general relativity, and there was everything. There was everything in that class. You got to use all the physics you had learned before. Well, this problem is the same way. You get to use many different branches of mathematics, which is always a good thing. So one set of questions is, and this comes from this belief propagation algorithm, if you run around transmitting estimates of the probability distributions from node to node, and you try to iterate on these estimates until you reach a fixed point, and in physics we call this the cavity method, but it goes back to the work of Judea Pearl in Bayesian inference and graphical models. Well, a silly thing could happen, which is where you hear from all your friends that they're equally likely to be in each group. And you do the math and you say, hey, I'm also equally likely to be in every group. So that's a silly fixed point. If we fall into it, then we're doing no better than chance. When do we fall into it and when do we not? And this turns out to be related to a classic problem in genetics, where you have a progenitor, an ancestor of a family tree. That ancestor transmits its characteristics noisily and imperfectly to its children. So its children are, the same as their parents, say with probability 60%, and with probability 50%, they're the other type, black cats and white cats or something. And then after many generations, I just show you the descendants, just the population of the descendants, and then I ask you to figure out whether the ancestor was black or white. There are phase transitions here, which turn out to be similar to the problem. And this is analogous to saying, I will be generous and will pretend that you know the true communities of the nodes at a certain distance away. Those are like your descendants, and then this root vertex here is like the ancestor. And as we try to propagate this information inward toward that node, it's like trying to propagate information backwards in this family tree. So depending on the parameters, sometimes the information survives and sometimes it doesn't. You also get to think about random matrices. So, how much does the community structure in a network affect random walks on the network or epidemics on the network? Mathematically, how much does it affect the spectrum, the eigenvalues and eigenvectors of, for instance, the adjacency matrix, the Laplacian, other popular linear operators associated with the graph? And I had to show you this picture because tomorrow's talk will be on the blackboard, and I cannot draw this on the blackboard. And this is the spectrum in the complex plane of a kind of random walk operator on the graph. And the question is, when is there an eigenvalue out here on the real line that tells us about the communities? Or when is it buried inside this disk where all the eigenvectors are just noise? Okay, so we get to think about random matrices, another good thing. And again, we get to think about what statisticians would call the hypothesis testing problem. If we have a null model and a structured model, how do we figure out which one the data came from? Which is the same as saying, if we think we've found some structure, how do we know it's really there? And this has to do with the likelihood ratio of the two models, and with some nice combinatoric techniques, we can bound the likelihood ratio and tell when we can do this and when we can't, or at least prove upper and lower bounds. Good. So you should come to the next two lectures, and thank you very much. Way in the back. Yeah. Uh-huh.
The one right next to it, I didn't understand the difference.
Good. So you're asking about this little regime in here. Yeah. So, okay, so down here, well, it's actually information theoretically impossible everywhere to the left of this line, okay? But below here, the landscape is pretty smooth and uniform in both the block model and the null model. In this regime, it's bumpy in both models. And the local optimum corresponding to the ground truth doesn't look any more convincing to you than any of the other local optima. So, the probability associated with that part of the space is not any greater. So even if you had the luxury of looking at all of the local optima, without some additional information, you would have no idea which one corresponded to the ground truth. What happens when we cross this line from here to here is that in this regime, the local optimum corresponding to the ground truth does have more probability nearby it. So if you knew about all of them, which we think would take exponential time, you would choose that one, at least with probability better than chance. So that's what's happening there. So it's at this line that the null model, the Erdős-Rényi random graph, and the block model become distinguishable. Yes?
Good example of what happened. I mean, this one you said it's like a glass, the middle portion.
So you're asking in physics terms, right? So in physics terms, both of these are spin glasses. The difference is that the structured model is what people call a planted spin glass. So how would that work? So, so suppose that I first choose a particular configuration, a spin configuration, of who's up and who's down, okay? I now choose the JIJs, the interactions, in a biased way. Okay, so this is a little bit like the Hopfield model of neural networks, for instance. So I choose the interactions in a biased way so that if in that planted configuration they're the same, then I choose a ferromagnetic interaction encouraging them to be the same. If they're opposite, I make an anti-ferromagnetic interaction there. Or I do that with some probability bigger than 1/2. So physically, this is sort of a strange thing to do, right? I mean, I don't think people thought of these models until work on neural networks started up. Because physically what we're doing is we're building in a particular state, building it into the interactions of the model so that that state will tend to have lower energy. So why would nature do this? I have no idea. Unless the state corresponded to there's some ground truth and then the interactions are somehow governed probabilistically, noisily, by that ground truth. So physicists in the spin glass community call this transition condensation. And it's also where the physics of that planted model will start to be different from the pure spin glass where the interactions are completely random. Yes?
Is significant in the vanishing, the rate of the vanishing. I don't know whether the curve, for instance, in the k equal to 2 case, you had a curve which sort of went down to 0. Where, so in phase transitions, those signify universality classes, and there are exponents there which are significant. Is there an analog in these cases, and it's significant?
Yes. So. Thank you for asking that question. So for two groups, this is a so-called second order transition. And let's see, I need to be a little, in honor of my CS theory friends, I want to be clear about which things are known in the physics sense and which things are known in the mathematics sense. I think what I'm saying now is the former and not yet the latter. Most of what I've been saying is the latter, but not all of it. Okay, so most of what, we know most of it now with a capital K. So anyway, all right, back to the story. We know or strongly believe that for two groups, the accuracy that you can achieve with optimal inference all the time in the world goes continuously to 0 as we approach this transition. And because this is the so-called mean field setting, an infinite dimensional setting, I think we would guess that the scaling exponent here would be 1/2, that it would look like a square root. And this is also the same way like the giant component in the Erdős-Rényi model looks, and so on. So whereas when we have more groups, this is a first order transition, we think that this is discontinuous. And so that what you could do with efficient algorithms would suddenly jump here. And this happens in random graphs as well. There's this thing called the 3-core, which is the size of the smallest subgraph where everybody has 3 neighbors within that subgraph. And that also has a discontinuous jump when the average degree of the random graph passes a certain threshold. So yeah, so here I think critical exponents would be the mean field ones, although what's happening here is a little more mysterious. I'm not sure about this one.
And are there other problems which are non-mean field?
Well, I think to get other exponents, you would have to have a model of networks with geographic structure. So we've had a couple of talks today and yesterday about, for instance, epidemics where you are more likely to infect people nearby you, which is of course true. And then, so if you have long-range interactions where the probability of an interaction, for instance, falls off as a power law with distance, then if it falls off too slowly with distance, then the mean field behavior will take over. The geographical structure will be unimportant and will be effectively infinite dimensional. But if they fall off quickly, then it'll really be, for instance, a 2 or 3 dimensional system. So in that case, I guess we would expect other critical exponents. If since as a physicist I was raised to think that it is always better to say something wrong than to say nothing at all, I will say they must be the same as the Ising model, critical exponents. Okay? By the way, I hope you take that to heart. So even when I'm training a student who is a theorem-proving student, I still try to teach them that it is better to say something wrong than to say nothing at all. At least you're moving forward the community's understanding. So you should never sit there silently and saying, but I'm not sure I can prove it. Conjectures are useful even when they're wrong. You students, remember that. Any other questions? Yes. Are you about to say something that you think might be wrong?
We'll see. So in physics, a powerful, unbiased, and systematic technique to extract patterns from noise is the renormalization group. So are there analogous techniques in other fields as well?
Well, it's interesting that you ask that, although I can't give you much of an answer. So, I mean, the renormalization group, as I understand it, sort of going back to Kadanoff, it makes the most sense when you have a spatial structure and you can scale that spatial structure down. So there are some papers just this past year where people are looking at multi-layer neural networks, the so-called deep learning problem, and they say that they can use renormalization group ideas there. And I don't understand it very well. I mean, I've seen a couple of talks. I think the idea is to trace over one layer of the network and to get effective interactions on the remaining layers of the network, and then to iterate that. I guess I'm confused, though, about how this really works, but it might work. So I'm afraid that's all I can tell you.
Thanks.
Sure. I mean, if you remind me, I can try to dig up these papers. One paper is by Dave Schwab and his collaborator whose name escapes me. And then there's another paper. Okay, if you email me, I'll send it to you or help you find it. Any other questions? Yes.
So in the middle regime where it's information theoretically detectable but not, but possibly computationally hard, do any of the other algorithms actually converge but perhaps take a long time, or is that something funny going on?
So that's a good question. So so the way belief propagation works, as you know because you've seen versions of this talk 6 or 7 times, the way belief propagation works is you typically initialize the messages, these estimates of the probabilities with which each node belongs to each group. You initialize that maybe randomly, and then you iterate and you reach some fixed point. So what we believe in this regime is that almost all initial messages converge to this silly fixed point, where everybody is equally likely to be in every group. Okay? So we think that in the high dimensional space of all possible messages, or combinations of messages, that silly fixed point has a huge basin of attraction, and that if you initialize with random initial messages, you will almost always fall into it. Meanwhile, there is also a very accurate fixed point, which is strongly correlated with the ground truth. If I showed it to you, you would say it has lower energy, or for the experts, free energy, but let's not worry about that. So you would choose it if I showed it to you. You would say it's associated with more probability. We believe, unfortunately, that it has an exponentially small basin of attraction, so that you would have to be exponentially lucky to start out close to it if you initialize things randomly. So then you can do other things. You can say, well, suppose that I tell you a certain fraction of the labels for free, or for all of the nodes, I give you what the physicists would call an external field. I'll give you a little bias pointing toward the truth. Then maybe when that bias or that initial information is strong enough, then suddenly that pushes us into this good fixed point. And then you can write more papers about a curve where this transition happens, where this axis is the density of the network and this axis is how much information I gave you. So there are lots and lots of phenomena like that. Now, we do not have a proof in this regime, though, this claim that most initial messages will evolve toward this uniform fixed point. So that's a well-defined mathematical conjecture, which I think would be really great to try to prove. Another thing you could try to prove is that if you were doing a Monte Carlo algorithm with so-called metropolis or Glauber dynamics, where you go around trying to flip which group individual vertices belong to, you could try to prove that it would take you exponential time to find those good, accurate states. In physical terms, that there is a big free energy barrier that you would have to get over. In probability terms, that there is a bottleneck there that would cause the mixing time of this random walk to be exponentially large. That's another well-defined thing that we could try to prove. So, I mean, even though we don't know that P and NP are different, we could certainly try to prove for certain classes of algorithms that they take exponential time here, or that each time we run them, they succeed with exponentially small probability. So, I think the one class of algorithms that we really know fail here are spectral algorithms, because you can show in this regime that all the eigenvectors are essentially uncorrelated with the ground truth. Any more questions? Turn it on.
Okay, so there are two follow-on lectures Chris is giving tomorrow and the day after, the same time, 4 o'clock in the Ramanujan Hall. So those of you who are interested should come. And also one more thing I want to mention from the side of the workshop organizers and everybody, we are very grateful to ICTS and for supporting this workshop. And this is a wonderful lecture series. And we've had terrific support from Rajesh, Avinash, Mansi, and others. So, the clap that we do now, I want it to be for them also. So thanks.